Welcome, everyone. If you could take your seats, we'll get started tonight. This is gorgeous. Thank you, UC Merced, for welcoming us here tonight with beautiful facilities. My name's James Lawler. I'm the founder of Climate Now. We are an educational multimedia platform. We produce a weekly podcast, as well as partner with others on events like this. ClimateNow.com if you're interested. And I would like to first of all thank our partners, Livermore Lab Foundation, the Lawrence Livermore National Lab, and all of the partners associated with this magnificent report. Once again, thank you to everyone who's here in the room, and we have quite a few people online as well, so thank you guys for being here. So just a couple of reflections before we get started. It is really it's not every day that we can be part of conversations that are like this. In this room and online, you have some of the smartest people in the world who have collected here today and who have done the research that we're going to be talking about. You also have the policymakers, the regulators who are designing and implementing the rules by which society will function and functions. And you have industry, the people who are creating the jobs and economic opportunity to shape the world that we live in and will live in the future. And the reason that we're all gathered here is to solve a problem that unites all of us, which is the problem of climate change caused by CO2 emissions from human sources. So the United States has a goal, which is by 2050 to achieve net zero emissions. What does that mean? It means that by 2050, the amount of CO2 that we are putting into the air and the amount that we are removing has to be the same, so net zero. How do we do that? Well, the most important thing is emissions reduction. This is well established. We have to reduce the amount of CO2 that is coming out of processes that we use to function in our society. So transportation, making the things that society uses to function, etc. But critically, we also have to remove CO2. We've been releasing it since the dawn of the Industrial Revolution. We're going to continue to release it. We have to remove it as well. And that's what Roads to Removal is all about. So we're joined here, and I'm going to introduce her shortly, by Jennifer Pett-Ridge, who is an indomitable force of nature in human form, who has led a magnificent collection of 68 scientists to create this Roads to Removal report, which looks at how much CO2 can we remove. And what it finds is something very, very hopeful. It finds that we can actually use technologies that we know work today to remove at least 1 billion tons of CO2 by 2050, and probably more, and in the process create hundreds of thousands of jobs. So this is a fantastic thing, and the reason we're here today is to learn about that. How exactly is that going to be possible? By what mechanisms? So that we can go forward into the world and figure out how to do it, and figure out together how we can make the world that we want to inherit and that we want to pass down to our children and grandchildren. So this is incredibly exciting, and it's so rare that we get to collect a group of people like this and have this conversation. We're excited to bring this event to cities and to regions around the country in the months ahead. And so without further ado, I'm going to introduce our first speaker tonight, who is going to set the stage when it comes to carbon dioxide. So Teamrat Ghezzehei is here tonight, and Teamrat is, I'll pull up your bio. Thank you. Teamrat is professor of soil physics here at UC Merced. And Teamrat, I'll welcome you to the stage now, and you can take the mic. Thank you.
I guess I can use this, right? Thank you, and welcome to Merced. My goal now is to set the stage, like James said. What I'm going to try to do is explain some of the simple facts and basics of carbon cycle, so that we all can follow Jennifer's presentation together in full. So some of what I'm going to say might be a review for some of you, but nevertheless, I want everybody to be on the same page as we go through tonight's conversation. And I also want to add some local context so that for the people who are from around here, you can relate to how this report applies to us. So I'm going to start from the basics. CO2 is a very important gas in our atmosphere. For a long time, for about 10,000 years, just until about 2 centuries ago, it stayed steadily at around 250 parts per million in our atmosphere. And CO2 plays a very important role in our climate. I'd like to imagine CO2 as a blanket that traps heat that goes from our Earth. To illustrate that, I made this AI art. So the blanket is CO2, the Earth is our Earth, and every day the energy that we release, some of that is trapped by CO2. And that's very important because it stabilizes our temperature, the temperature that we got used to. Everything that we take for granted, our forests, grasslands, water resources, our centers of population, all evolved in adaptation to these 250 parts per million CO2 over many, many centuries. But since the start of the Industrial Revolution, we started adding more CO2, and this has been accumulating steadily, and especially since the end of World War II, it has been increasing at a very steep slope. Right? Right now we are at 420 ppm, parts per million, and if you extrapolate that, it looks like we are headed towards 450 soon. Right? So why should we worry about that? Well, like I said, it's a blanket, and a blanket adds heat, and we are already seeing the effect of this added thickened blanket of CO2 in terms of temperature rise. Just in the last 50 years, the temperature has risen by about 1 degree on average globally. Right? So when I tell this to some of my undergraduate students, the question they ask is, but does it really matter? 1 degree is just 1 degree, right? In one day, just today, the temperature between the maximum and the minimum is more than 10 degrees C, right? The way I would like to imagine this temperature is not just as a daily temperature fluctuation, but as a symptom of a larger problem, right? Our body temperature is about 98.6 Fahrenheit, right? 37.5 degrees Celsius. When the temperature rises by 1 degree, 1.5 degrees, right? We're not really worried about the temperature per se. We're worried about the underlying issues that this symptom is signifying, right? In the same way, when the temperature of our Earth goes by 1 degree, 1.5 degrees, what we are seeing is the residual effect of the heat that was trapped by CO2. In fact, a huge fraction of the heat that we trap by CO2 goes into moving air faster, longer distances. It carries more vapor, and as a result, you have more floods, more droughts, and many other things. So what I wanted to do briefly is just to show you some of the key examples of the effect of a 1.5 degree warming or 2 degrees warming. And I chose 4 examples, 3 that has some local significance, right? So the first one is at 1.5 degrees C increase above the pre-industrial average would translate to doubling of the flood risk that we encounter every year globally, right? And another 0.5 degree warming will increase flood risk by 2.7 times, right? That's a huge increase in flood risk. The number of days or the number of people who will experience extreme heat wave at least once every 5 years will increase to 14% at 1.5 degrees C, right? 14% of the world population. That is more than 3 times of the US population. At 2 degrees, that will go to 37% of the world population will experience extreme heat at least once every 5 years, right? That's very bad. Insects that are responsible for pollinating a lot of our agricultural lands here in this valley will start losing some of their habitats. At 1.5 degrees C, 6% of insects will lose half of their habitat. At 2 degrees C, that will be translated to 18% of insects losing half of their habitats. Right. And a fourth example, a global example, is the Arctic will be ice-free at least once every century. If we go to 1.5 degrees, right, that's once in a lifetime. But if we go to 2 degrees, it will be several times in a lifetime, right? So these are the symptoms, these are the underlying problems that we worry about. It's not just the temperature, 1 degree or 2 degree, right? A big source of this problem is the fossil fuel that we release. And in the report that Jennifer is going to share with us soon, you'll see some large numbers. So and I thought I would simplify and give you some rules of thumb too, so that the numbers can be relatable. So if you take a gallon of gasoline and you burn it, it produces 20 pounds of CO2, right? 1 gallon, 20 pounds of CO2. If you burn 100 gallons of CO2, that means 2,000 pounds. That's roughly a ton, right? The US in 2022 released 5 billion tons of CO2. So you can do the math, how much gasoline that translates to, right? So when we talk about large-scale CO2 removal and CO2 release, we are talking about billions, right? Billions of tons, but a ton, I think, is a good rule of thumb to remember. A ton of CO2 is the equivalent of 100 gallons of gasoline, right? So the next thing I want to talk about is just the general flows of CO2 into and out of the atmosphere. And I'm going to pick only a handful of the main sources. Right, so first, fossil fuels and industry, the ones that we use every day in our lives, release on the order of 7.7 billion tons of carbon. If you've noticed, I've changed my units now. I was talking in CO2, now I'm talking in carbon, because we don't really store CO2, we store carbon in plant biomass and in soils. Just as a reference, at the bottom I gave you 2,000 pounds of CO2 is made up of about a quarter of that is carbon. Okay, so we release 7.7 billion tons of carbon annually in the form of fossil fuel burned, another 1.1 billion when we have forest fires or we change our land use, right? So that's net addition to the atmosphere. Plants, this could be natural plants and agricultural plants all combined, they pool about 120 tons of CO2 and they push about half of that to the soil, right? And when these plants respire, they release a huge chunk of that, but we gain about 2 billion tons of carbon that remains in the soil. In the same way, oceans pull out 92, they release 90. When you add up all these, what you see is about half of what we release is actually compensated by what nature does, what nature pulls down, right? But this is only in 1 year, right? To understand the full magnitude of our problem, I think you have to look back to what we've been doing since the Industrial Revolution. So when you look at, this is the annual release of CO2 that we've been sending to the atmosphere from fossil fuel burning, right? So now I come to today's topic, right? So our problem is huge in magnitude. If we are going to stabilize our climate at a 1.5 degrees C by 2050, we need to balance the emissions with the removals. Those two have to cancel out. We have to have net zero release of CO2 to the atmosphere, right? And we can do that only through two main ways. One is we have to reduce our emissions, right? It's the number one strategy, but we can't eliminate all emissions. There are some things that we can't eliminate. And to compensate for that, we have to increase our removal. Okay. So the report is gonna goes through so many options for removal. I will very quickly give you 3 examples that have some local relevance. I'm going to start at the top of the Sierra Nevada, and then I'll end up here. And also in the process, I'll mention some of the researchers here at UC Merced who do work on these topics, right? The snowpack on Sierra Nevada is the water tower that feeds our agriculture, our cities, our population, right? The snow melt. And researchers have been looking at the forest use of some of this snow water and have realized that the increase in forest density in the last century has been reducing some of the water flows that comes down to the valley. You know, it has also increased fire hazards. So there are studies that show that thinning the forest will help with fire risk, will improve water yield, but also if we take that biomass and somehow we convert it to some useful form that stays in the soil for a long time, we can get climate benefit, right? So one way of doing that is you turn that into charcoal and you add it to soil. You could do the same thing with the agricultural waste biomass. We are surrounded by ag lands, including almond orchards right around here, campus, right? If you take all that biomass that comes out of all these agricultural lands and you convert that to biochar, this is just one way of using these. Half of that carbon is stored in the char, and once you add that charcoal to the soil, it can last for decades to centuries, right? So it's an excellent removal process. And in the process, you benefit many other side effects, including water and nutrient retention. And lastly, you can change the way you do agriculture. For example, you can grow cover crops in winter using the rains like that we had this afternoon without using much irrigation water. And in the process, that cover crop would add more carbon to the soil. If you, in addition to that, you reduce your tillage, you can start accumulating carbon in the soil. This is a result from one of my collaborators, Jeff Mitchell, who's been doing this for about 20 years at a A&R experimental field. So all in all, we have options that we can use here in the Valley. But with that, I will stop for Jennifer to tell us more. But
thank you. Dr. Jennifer Pett-Ridge, Senior Staff Scientist, Distinguished Member, Senior Fellows at Lawrence Livermore National Lab, and leader of the team that put together this magnificent report. Dr. Pett-Ridge has published over 150 peer-reviewed articles, cited over 10,000 times by her colleagues in academia. She is a force. Please welcome to the stage, Jennifer Pett-Ridge. Thank you.
Hi, everyone. Hola. It's wonderful to be here. One other title that I have is Adjunct Professor at UC Merced in Life and Environmental Sciences. So it means a lot to be here, to be with you. So thank you to UC Merced for hosting us, to the many, many people who are in this room and online who have made this event possible. So I will tell you a little bit about this report that you've been given a nice preamble from my colleague and good friend Teamrat. Thank you, Teamrat. The number of authors on the report doesn't fit on a page, so I list some of them here, some of the leads, but I have to thank them for their diligence over the past 2 years that it took to put together this analysis that we call Roads to Removal, Options for Carbon Dioxide Removal in the United States. And maybe you've seen this figure or something like this figure many, many times. This idea that we need to stop the trajectory that goes up and we need to follow this line that comes down. where we are reducing our emissions. And it's funny, I see this figure so many times, and I was thinking about it earlier today. It makes it look easy. It's like a water slide. You just slide down, right? It's just easy. We just stop emitting. It's incredibly difficult to change our economies and the way we use products to stop those emissions. So I don't want to underplay how difficult it will be to decarbonize our lives, our economies. That's the biggest part of the equation. But even when we do everything we can, there are still parts of our lives and the things that we want to do. You want to get on that airplane. We need to make cement, steel for factories, for houses. We need these products, and we don't yet have a way to decarbonize, to take the fossil fuels embodied in those products and their production completely out of the equation. So there will be a certain amount of residual. You can see the gray never comes all the way down to zero. And we have to compensate for that. That's why we're here today. It's compensating for the fact that try as hard as we might, it won't be easy, and we won't get all the way to zero without literally sucking CO2 out of the air. It's as simple as that. It sounds simple, but it's not. How much do we need to do? Well, as you just saw some of the big numbers globally, we maybe emit something like 40 billion tons per year. We need to essentially be removing 10 gigatons, billion tons, those are the same, per year. By the time we get to 2050, not tomorrow, but starting tomorrow and getting all the way to 10 billion tons by 2050. But the United States isn't responsible for all of the problem and not responsible for all of the solution. The White House and many esteemed scientists at the International Panel on Climate Change suggest that 1 billion tons is what we're responsible for. So that's what also the Department of Energy has set as their Earthshot goal, just like we had the moonshot back when I was a child. We now have such an important need that they have established a funding and essentially level of enthusiasm throughout our government that we have to hit that target. Now, a couple of years ago, some colleagues at Lawrence Livermore Lab, I was peripherally involved, wrote an analysis that we called Getting to Neutral, because our governor had said, we want to be net zero in this state by 2045. And okay, that's great. Governor can say that easy peasy, but can we do it? So our analysis showed, yes, we can do it. We can do it by that time point. Here's how. Here's what it would take. Here's what it would cost. So that analysis inspired us to think, wow, if we can do it for California, what if we expand? Can we do it for the entire nation? For over 3,000 counties across our country, what would that analysis look like? And can we hit that 1 billion ton removal goal by 2050? So that's essentially the charge that we started with. And we had colleagues contribute, again, 68 of us, and including one undergraduate, actually not even an undergraduate, sorry, he's in high school. He just applied to college. He wrote to me the other day, a guy at UPenn who was contributing to this analysis. So very well-established scientists and very junior people came together to work on this project. All across the country, experts in many, many different fields. And what we first asked is, what's the capacity? Where can we do it? We want to try and understand that at the highest resolution we can. We call this a bottom-up analysis because while we used modeling, we started those models, they're parameterized by data that exists from the US Forest Service, from the Soil Survey, from our industry colleagues, from the folks who have done the math on how much CO2 can be stored in what geological formations. That data exists. You can access, it's public. And we gathered that to, again, to make a bottom-up analysis of the capacity. I mentioned this is county level. That's important to us. You'll see later that there's not a one-size-all-fits solution. Certain counties have more options in one versus another approach. We looked at several key approaches. I'll tell you more about that in terms of the different ways we can do carbon dioxide removal. And something that I'm extremely proud of, and I really think is a first of its kind, is we included cross-cutting analyses that heavily weight environmental, justice, and equity. We can't just foist new industries, a whole new way of making money and living and managing carbon onto communities that are not ready to hear that, that don't necessarily capture this, all of the science, but want to capture the benefits. So we need to weigh how these new approaches to removing carbon can affect our daily lives, our jobs, our revenue streams, our water quality, where the renewable energy is going to come from. That has to be part of the conversation. And then I'll finally just say this is not meant to be any kind of finger wagging, no policy recommendations. We really scrubbed the report from any "you should" kind of language. Here's the data. And the reason we're here tonight is to ask you to respond to what the data says. You may have insider knowledge. I'm sure you have insider knowledge to the County of Merced that I cannot have because I live in the East Bay. And so we have to have this dialogue about here's what the data says, but here's what you bring to the table. Maybe it's hard to store carbon in soil if you don't have enough water. Yeah, this has been an issue in the Central Valley. So we need to have that kind of dialogue. Here's the take-home story. Yes, we can meet the goal. We can absolutely remove 1 billion tons. We can remove more than that. I'm not going to show you all of the details. Tomorrow morning, if you come and listen to the more technical lecture, you can see all the numbers. But we can remove more than 1 billion. But let's just stick with 1 billion and what that would cost. 1 billion tons of removal would cost $129 billion. So $130, let's say, per ton, per metric ton. And I'll ask you something. What can you buy? What commodity can you buy for $130 a ton? You think of anything? The only one I've come up with is sand, because it's really heavy and not worth very much. So I think it's actually a pretty good deal, $130 a ton. I know it does sound like a lot of money. It's half of 1% of our current GDP. And what we're suggesting is that we need to start paying for something that is waste removal for invisible garbage. That's hard to get our heads around, the necessity. But believe me, the necessity is real. The costs of climate change dwarf this number. And there are benefits. We calculate something on the order of 440,000 new jobs in this country. Good long-term jobs distributed across the country, not just in the counties that are already advantaged, but in the disadvantaged communities as well. So let me tell you a little bit more about the 4 main ways of removing CO2 that we focused on. CO2 starts in our atmosphere. I think of plants as the OG of carbon removal, right? They know how to do it. They're far more efficient than we are, and they do it for free. So we can remove via trees and forests and croplands. That carbon embodied in the mass, the biomass of those plants, is held there for a period of time. In forests, it can be for several hundred years. If there's a wildfire, it can be for 20 more minutes. If those plants have deep roots, if they're perennials and they live year on year, they often put that carbon deep into the ground. I'm a soil scientist and I like to go out and dig soil pits. Some of these deep switchgrass roots go on below 3 meters, and I stopped digging at that point, but they keep going. They're putting that carbon away deep into the ground. So there are lots of approaches we can look at in just these ecological solutions for capturing carbon. But we can also take the biomass, the material that is above ground in trees or in croplands, some of it, which just naturally decomposes back to the atmosphere, it's part of the cycle that Teamrat described. If we collect that mass, if it's walnut hulls, if it's corn stover, almond shells, or maybe some of the extra trees in our forests in Northern California, we can take that to a biorefinery. And we can use all kinds of techniques that I won't go into a lot of detail on, but we looked at 27 different approaches that range from fermentation, gasification, pyrolysis, which is just really burning things under high pressure without oxygen. All of those processes designed to capture the carbon while maybe making hydrogen or bio-oil or biochar, making a product that will last and that we need to drive our economy as a replacement for the things that we are losing if we give up on fossil fuels. We call that process BiCRS, biomass carbon removal and storage. But it's about taking what plants have captured and creating useful products. It's valuing the carbon in that mass, not just the electrons that we can make from burning it. Now, one last thing that I want to mention is direct air capture. And often when you hear about carbon dioxide removal, this is the one that people are talking about. They skip all the way to the most expensive part. Direct air capture is literally using a kind of vacuum cleaners and chemistry to suck atmospheric CO2 at atmospheric concentrations, 400 and some ppm, from the air. Using solvents, different chemistries to capture that, concentrate it into a supercritical liquid CO2, and then taking that to an injection point where they can inject the CO2 deep below ground, a mile more below ground. It's expensive, but it's also something we know how to do. All of these approaches are what we would consider mature. Now, there are many more. So the approaches that we analyzed are the ones we have in color at the top there. Everything in gray are great ideas that scientists have. Probably here, people on campus here are studying some of things like ocean mineralization or the enhanced rock weathering if we add basalt rocks to our farm fields, or things that we can do in managing peatlands or biochar. I love all of it. I'm a scientist. I want to study that stuff. We didn't include it. We didn't include it because it didn't feel reliable and mature enough. And again, we needed a bottom-up analysis. We needed to have data for every county, or most every county in the country, to be able to do the analysis. So we left a lot out, which is why it's so kind of amazing that we still hit our target. We go beyond our target, even with today's, or 2 years ago, technologies, because honestly, we made decisions 2 years ago about what we were going to do an analysis of when we started. We have multiple guardrails as well that I'll tell you about as I go through the process. But I'm going to start with soils, because I'm a soil scientist. I got to start there. And this is a map I always love to show. It's by my friend John Sanderman, who did a calculation of how much carbon we've lost from agricultural soils on this planet. We practice agriculture on nearly half the land surface of our planet. Every time I say that, it's mind-boggling how much influence we have. And when we till soils to plant crops for food, fuel, fiber, we lose carbon. Some of it we lose to erosion. A lot of it we lose because you're putting microbes in front of their lunch. And they're respiring the CO2. And we've lost something like close to 500 billion tons of carbon as CO2 equivalents into the atmosphere. That's a third, if you were to take that number, of all of the emissions. Now, realistically, we can't quite make that equivalency because some of that carbon may have been lost to erosion, but it's a huge number. We have a debt to our soils that we should repay, I would argue. Anyone here involved in agriculture knows that carbon means organic matter. Organic matter means water holding, means nutrients, means biodiversity, means more crop productivity. So putting that carbon back in the ground is a good idea, not just for carbon removal reasons, but lots of other reasons. So carbon on our agricultural soils is the tip of the iceberg that our soils are telling us about their sensitivity to the climate, but our soils are also an opportunity for carbon and climate mitigation. And so analysis done by my colleague, Allegra Meyer, looks at croplands across the United States. And she and her team focused on 3 really reliable ways to achieve carbon increases in soils. They looked at many, and they chose these 3 as the ones they felt could be done in the most places and most reliably increased soil carbon. And they are cover cropping, or planting crops in the wintertime when you aren't growing a cash crop, perennials that are carbon crops. Those are more relevant in the central part of the country than they are here in California, but plants like switchgrass, native grasses, miscanthus, often grown on marginal land that's not being used for any kind of food crops. And what we call perennial field borders, and that means, you might have heard of shelter breaks or planting trees or shrubs, hedgerows around the edges of crops, and that's been done for centuries, mostly to manage erosion, but as a kind of a living fence, really. And just those little bits of perennials, those plants with those deep roots, make a difference in terms of capturing carbon. Now, the analysis results that you're looking at here, these wonderful sort of skyscrapers, reflect how much capture is possible. Most of it is in cover crops. If you can't see the numbers, they decrease by an order of magnitude as we go from cover crops to perennials, carbon crops to the field borders. And one thing I'm going to have to apologize really for you here in Merced is that we looked primarily at row crops that were of the 6 top commodity crops in this country. And unfortunately, that leaves out a lot of California. So if you come tomorrow morning, you're going to see some new analysis that Allegra did of what might be the case in orchards and in some of the more common crops here in Merced County. But if you look here on the map, I know it looks like there's not a big opportunity in California. And that's, again, just because we put some guard rules on that kind of left that out. The take-home message across all of the country is that by 2050, we can remove 130 million tons if we pay that farmer $40 a ton. If that farmer asks for a little more, $100 a ton, then we're up near almost 1 billion tons of cumulative removals by 2050. So that's important, just that fact that what we pay matters. Of course it does. That's true in all parts of our lives, but we need to include that calculation, that there needs to be an economy, that somebody's got to make money before they're going to do an action, whether it's planting cover crops or not. Even though many, many farmers in the country do, I believe it's about 6% overall of the country are using cover crops in a routine way. Let's talk a little bit about forests. A lot of forestry going on in the state, a lot going on in the West, a lot in the southeast of the US. Forestry, simply for collecting lumber, is an important part of our economy. But there's a lot of waste associated with forestry. And even more than that, particularly in California and the West that is so fire prone, as we all know, we have many forests in the northern part of the state and in the Sierras that have 3 or 4 times as many trees as they should. Back when ecology was managing our forests, when our native indigenous colleagues were managing our forests, we had many fewer trees. There was space in between them. And forest fires that got up into the crown and got completely out of control were less regular. And we know what the effects are. You know it here because you are even closer than I am in the East Bay, but you feel the particulates in the air. We see the loss of property and, to be honest, loss of life that comes from the mismanagement of our forests. So there's a lot we can do in managing forests to better protect them. And what this data shows is for the state of California, the opportunity in terms of, these are at the bottom, thousands of tons of CO2 removals, simply by managing forests, by doing these thinnings. And it's a little counterintuitive to think that, okay, by removing trees, I can actually store more carbon, but it happens to be true because they're less at risk of burning, where we lose it all. The other neat thing about removing biomass from a forest is you can use that waste material to make useful products. So that leads me, again, to this concept of BiCRS, or biomass carbon removal and storage. And I'll just say that forest residues are the biggest opportunity, the biggest kind of waste in our state. But we've got plenty of ag residues too, and a lot of that is just, it used to be burned, now we're not allowed to, right? A lot of that's just decomposing, going back to the atmosphere. Municipal solid waste, everything I put in my green bin, and we all do, currently gets trucked to a landfill most of the time, sometimes composted, but still it's just going back to the atmosphere. What if all these wastes were collected and used in one of those processes I mentioned, pyrolysis, gasification, fermentation, to make useful products, to make hydrogen, to make bio-oil, to make bio-asphalt, biochar? Again, there are a lot, I could go on, but we won't go into all the biochemistry. The point is we can make useful products and at the same time, and probably more importantly, capture the carbon. That carbon is then going to need to be stored, and most of the time we're thinking about geologic storage, which I'll get to in a minute. But this is the biggest opportunity across the entire nation, somewhere between 700 and 900 million tons per year, and it is a set price of approximately $100 a ton. And this is something that will take investment. Everything I told you about forests and soils, we could start tomorrow, literally tomorrow. These BiCRS facilities need to be built. And we'll have a conversation afterwards about how much they cost per facility, but it's a big number. So that's going to take investment, and that's not going to happen tomorrow. But by 2050, we can get there. And we have the waste, instead of trucking it to a landfill, what if we use it as a useful product? Now, I told you about needing to store that carbon durably. So we need to talk about geologic storage. And we made this drawing to try and emphasize how deep we're talking, 1 mile to 2 miles below the surface. In certain rock formations, we can store CO2 in the tiny, tiny spaces between individual mineral particles. This isn't a big lake of high-pressure CO2 beneath the Earth's surface. This is within the finest grains you can really imagine. And over time, that high pressure actually converts the CO2, it mineralizes, it becomes part of the rock over decades to centuries, timescales. So it's really an incredibly safe form of storing carbon. So we made an analysis of not only where are the geologic formations in sort of 2D, which I know that's what the map looks like, but what's the volume in each place that we can inject CO2 into? What's the top and what's the bottom of that capacity? And we have excellent geologic storage in something like 22% of the nation. We have potential storage that might get us even to sort of half the country, 50%. So when you look at this map, all of the places that are green, and probably some that are in the yellows, the perspective, have the potential for geologic storage. Now you're probably honing in on California, right? In the Central Valley, we have excellent potential for geologic storage. We have the right kind of rocks. Our analysis didn't just look at where we can do it and how much, but we looked at how much will it cost to monitor an injection well for the next 20 years, because we need to do this safely. We need to make sure that there aren't leaks happening, because that's counterproductive. And we show that those costs are minimal. So lastly, I want to talk about direct air capture. And again, I'm not going to get into quite all the chemistry, but just to say we have both liquid and solid ways that we can capture CO2. It then takes energy to desorb that CO2 that we are going to inject below ground. That energy we insisted be renewable and be built specifically for that facility right there, not dragging it off the grid and making your and my electric prices go up. We also insisted that these facilities be located near good geologic storage. And so that meant that there were really a limited number of places in the country where it's appropriate to think about direct air capture. Most of them are in the Intermountain West. There is some opportunity here in California, but I'll emphasize that our land costs are high. We can do renewable energy. We have geologic storage. We have the know-how to do direct air capture, but there are only certain places in the state where it's going to make sense for all of the reasons together. Now, last I mentioned that we did an analysis that we call the cross-cutting, where we looked at all of the resources. Where is there land and water and available renewable energy? That was the analysis that helped us pin down where can we really do the direct air capture most efficiently. But the last thing I want to talk about today is environmental and human justice. So what we call our EEJ, so energy, environmental, equity, justice. And there we looked again at a whole series of different indices. I can't go through them all, 26 different approaches or different indices of the health of people and the environment. And here are just 3 options. We looked at the social vulnerability. That's a mixture of both the paycheck, what people are taking home, and also their health outcomes. We looked at soil erosion. That's something we want to minimize. We also looked at PFAS. These are the forever chemicals that are in a lot of products that we buy and that have really negative outcomes both for human health and environmental health. So we had to weigh all of these things, and we looked at where can we apply carbon dioxide removal that improves the good and decreases the bad. It's as simple as that. And Kim Mayfield is here and would be happy to tell you more. I'll just wrap up by saying the answer for the whole nation is complex. Every region has a different opportunity. There's no one cookie cutter approach that we can apply everywhere. We don't have croplands everywhere. We don't have forests everywhere. We don't have biomass or geologic storage everywhere. So that's why it's so critical to be here with you tonight and to be telling you the story specifically about this state and the opportunities here. We'll be going into those in much, much more detail starting tomorrow when we have the technical talks and roundtables. But what I want to leave you with are the real opportunities that we do see for the state of California, and particularly for the Central Valley. And that's that the agriculture core of the state has real opportunities in this sector for cover cropping, for using those wastes that are currently, well, used to be burned, but are currently just being allowed to decompose or have to be trucked off-site, using those to make useful products, and also for doing CO2 storage, particularly down in the southern part of the Central Valley where there's real expertise in that area. Managing our forests, both to make them more healthy and less likely to burn, and also to use the extracted biomass, again, for those useful fuels like hydrogen or biooils. And lastly, we have even some opportunities for renewable energy that are rare elsewhere in the country. We have geothermal energy opportunities down near the Salton Sea. All of this together means we have an enormous opportunity in California. But that doesn't mean we can just flip the switch, does it? We need to have community conversations. We need to talk to policymakers. We need to have conversations about environmental justice and about jobs. All of these sectors need to come together, which is why it's so important and so exciting for me and our team to be with you tonight and tomorrow to start this dialogue. So I'll end by again thanking the team. This is most of us when we gathered about a year ago at Lawrence Livermore. I also want to thank the support folks who made these beautiful images, right? All those beautiful maps, and helped us put together a booklet. If you'd like a copy of the executive summary, we have that here tonight. I want to thank Susan and the team from the Livermore Lab Foundation who were able to raise additional funding so we could do this engagement with you and around the country. And again, originally from the Department of Energy, who had the idea to fund this project and bring this to you. Thank you. Let me say it one more time. The recording of tonight, all of these slides, will be available on that website. There's already great stuff there, short little videos, teaching tools, fact sheets, interactive maps, so you can go and look at your county. But yes, it is for you. It's funded by the taxpayer and it belongs to you. Yeah.
Thank you very much. And I do want to thank our supporters tonight who made this lecture and our conversation and this event possible. Grantham Foundation, ClimateWorks Foundation, and Breakthrough Energy. Thank you very much. So, yes, round of applause. Thank you, Dr. Pett-Ridge. Thank you, Dr. Ghezzehei. So this is going to be an interactive conversation. So if anyone has questions or think about what you've just heard, come up with questions. I'd like to call on the audience as we have this discussion. But Teamrat, I'd love to start with you and a question. We've talked basically mostly about two stories here. One was soil carbon and removing carbon through the soil, and the other is BiCRS, right, through biomass. And both of those are relevant to this location where we are today, Merced. First, we have two soil scientists here, but Teamrat, you study soil physics in particular and the physical processes that occur within soils, one of which is carbon dioxide removal and storage. Explain how that works. So, most of us have this idea, as Dr. Pett-Ridge described, plants absorb the CO2, they create biomass, and it's stored there. But carbon dioxide also is released from the soil, and it's a balance. Tell us about what exactly is happening in soils to achieve the removal that we just heard about.
So removal from, okay. So two things. Soil does not suck CO2 out of the atmosphere on its own, right? It takes carbon out of the plants. And if the conditions in the soil are right, then some of that carbon can stay in the soil for a long time. But in an agricultural land where you frequently irrigate, in our case, in these days, you also create a condition that is conducive for the microbes to degrade, consume that organic matter. So
the microbes, what microbes are we talking about?
So bacteria, fungi, and maybe some other larger organisms as well.
Okay.
That take energy out of that organic matter, right? So they decompose that, they eat that, that's how they survive, they take the energy. And in the process, just like we burn fossil fuel in our engines, they burn that organic matter and they respire CO2, just like we do. There are some practices that we do in agriculture, like tillage, which is helpful for increasing infiltration, tend to also increase the availability of air, oxygen for the microbes.
And what is tillage?
Tillage is basically the practice of breaking the soil using machinery of some sort or animal-drawn devices to break up the soil clods so that you create more porosity, to make the soil easier and softer for plant roots to grow, for water infiltration to go deeper into the soil profile. But at the same time, you also create this porosity that allows air to go into the soil and makes the microbes happy. And if they're a little too happy, then you lose more carbon than you should. So that's basically what you try to manage.
So it's a complex dynamic that involves a lot of different factors. Yeah. Now, you've been involved in a number of studies locally that have looked at carbon dioxide or carbon retention in soils over a period of time here in this region, right? Can you tell us about those studies? Like, what have you found in terms of, carbon removal and the potential of these agricultural lands to do the things that you've just described?
Okay, so one example is, as I showed a picture towards the end of my talk. This is a work that was led by my collaborator, Jeff Mitchell. He's an extension specialist with the UCANR at the West Side Experimental Station here in the Valley. And for about 20 years, he's been conducting an experiment that I was fortunate to join and do some measurements. And what he has done is he looked at reducing tillage, the disturbance that I just mentioned, and also adding cover crops. And everything else being the same, like what a typical farmer would do, but with the addition of cover crops and reduced tillage. And over 20 periods of time, a 20 years period, you see a significant accumulation of carbon in the topsoil.
So 20 years.
20 years.
So this is not something that you roll out the cover crops and you've got the carbon and you're done.
You get, but it becomes very difficult to see, right? So it's that you're adding a lot and you're removing a lot. So to see the effect, you need a few years before you start seeing the incremental addition of those tiny amounts.
Got it. So it's an accumulation over time of the carbon that is stored in the soil. Dr. Pett-Ridge, I wonder if you could talk about, why do this? So when we're actually, these conversations are about, the report has shown us what's possible, and now we have to move to how do we make this a reality? How do we actually get, farmers to see it in their interest to do this at the scales required? So I'm wondering if you could speak to the reasons that this is useful beyond the slow accumulation of CO2 and all of the the benefits that we know CO2 removal will confer. What else? Why else should this happen?
Right. So first of all, cover cropping, maybe it sounds easy. It's complex. It is a dance between when you plant your winter crop and when you harvest your cash crop. And all farmers that I've met are really keen to use the practice. Many of them use it in some years. I met an individual who was managing the farm that my family owns in Nebraska, and he says, we do it as often as we can, but some years we run out of time because it starts snowing. Here in California, it doesn't snow too often in our fields, so there's a real opportunity to do it, but again, it's complex and when it needs to happen. And which crop you plant. I was with a series of organic growers last Friday who said, we really like to plant 5 different types all at once. Well, that's complicated. And we don't, as an industry, the agricultural industry has not embraced cover cropping as routinely as they could. In our orchards, as we were driving here, maybe 1 out of 3 had a cover crop growing in between the rows. And I think that there's some misconceptions that maybe those cover crops are going to steal water from the trees. Turns out that's not true. But there are lots of good reasons that our producers know are reasons to put these cover crops on the ground. And that has to do with, again, putting more organic matter in, holding the soil. The last thing an agricultural producer wants is to have erosion. And that's one of the main reasons we can cover crop.
Does anyone have any questions yet, right off the bat? Please. I do,
but it's not about soil.
Oh, that's okay.
So I'm with Phoenix Energy, and we build BiCRS plants in the Sierra Mountains. And BiCRS is a term that's been around for a while, and now we have BiCRS, and I'm struggling with trying to understand the BiCRS versus BiCRS, because we do see ourselves as a carbon removal company. We do remove significant amounts of carbon. So I was just wondering if you could shed some light on how you think about BiCRS versus BiCRS. And
yeah, and Lonnie, would you mind just describing your process at Phoenix?
Oh, God.
Sorry, just briefly, just so people understand
Sure.
what Phoenix does, so
Sure.
that we can answer that question.
Yeah, so we think of ourselves as a carbon removal company, but energy is our primary product. So we operate in 3 different markets with our biomass residuals, which is agricultural, forest, and landfill. And we use those residuals to, as fuel in our plants, and we use a very sophisticated gasification technology and turn that into valuable products, much as what you talked about here on the slides. So we produce 24/7 green firm power, renewable energy, which we sell to PG&E, and we produce biochar, which you talked about a little bit in your slides, and we also have carbon credits as a result of all the carbon removal, avoidance, and sequestering work that we do with our plants.
Great. JP, do you want to take that one?
I'd be happy to. So these acronyms, BECS, BiCRS, they're really ways we can use biomass. And what we see is the difference in BiCRS, this term that I was talking about today, is we put the carbon removal first at the top of what we want to achieve. That's the most important. So we're optimizing the process for the carbon removals. And it's not to say that the practices that you're talking about in BECS, which is typically more about producing a fuel, which might be electricity or a gas fuel or a hydrogen fuel. It's just instead of putting that hydrogen production first, it's putting it second in the list of things that we're optimizing for. And that's largely because of something we sometimes jokingly call the Ains principle. And Roger Ains is here in the room,
Roger
so
Ains.
I'm gonna point to him, which is that if we think about all the work the plant has done to fix that carbon, let's value that mass for its carbon, as opposed to just for the electrons that we can gain as we burn it. We get a lot more financial benefit as well, and benefit to the climate if we put the carbon first in removing the carbon. So it's mostly about how we do the math and the life cycle analysis, the system analysis. But I personally think that the acronyms, they hold people away from understanding what the process is. So I prefer it when we can just, as you did, describe the process and the value proposition that your company is involved in, which is great.
And thank you for the question, Lonnie, and Phoenix Energy for being here. We're really fortunate to have quite a few projects that are local, that are doing some of the things that you have seen here tonight. And we're going to call on some of the other project developers tomorrow to learn more and really get into it. Do we have any questions from the online audience? We do?
Yes,
Yeah.
so we'd like some clarification between carbon removal and CCS.
Great. Who would like to take it?
Sure, sorry, Teamrat. We're gonna make sure Teamrat got some questions too. Carbon capture and storage is what we use when we're talking about typically point sources of carbon. If you're at a refinery and there's loss there, if you're at a coal plant that's being retrofitted, a lot of industries these days are looking at really high concentration streams of CO2 coming out of the stack. And if that's being captured, that's carbon capture and storage. That's great, we gotta do it, it's important. But it's not a net removal. So that's the difference between carbon dioxide removal, or what we call CDR, where we're trying to literally take CO2 that was in the atmosphere and net remove it from the atmosphere.
When you say net removal, just explain that one more time. Like when the concept of net removal versus capturing it off a flue stack, because it's a little bit nuanced. And
so let's think about if we're using coal,
right,
which is, to be honest, an outdated technology. There's less and less. But that coal the carbon in that coal was fixed. I'm not a geologist. It was fixed millions of years ago.
Dinosaur
right?
poop.
Dinosaur poop, yes. And so that carbon is not really in the active carbon cycle right now. So if we're taking that out of the earth and we burn that and that CO2 is lost, that is going to increase those emissions, that 40 billion tons that are entering our atmosphere every year. That's an increase. So if we capture some of that, we're just getting back to the baseline, really. Even if we captured 100% of it, which I'm not aware of any technology that gets us to 100. Most are in the tens of digits. Mm-hmm. So that's just, it's not actually getting us Remember how I showed the 0 line and I said we needed to really go negative? That's not getting us into the negative zone of
Yeah.
removal.
I want to ask another soils question as it pertains to this region. Teamrat, one of the main concerns is, of course, water, and Dr. Pett-Ridge alluded to this in her talk. What is the impact of reduced amounts of precipitation, water here on soil's ability to retain carbon? And how should we think about that?
Yeah, so again, going to the plant story, plants are the pumps that will suck the CO2 out of the atmosphere. So if you don't have water, you don't have that ability to bring it down. But for almost all the solutions that we've been talking about today is we're growing plants anyway. We are practicing agriculture, not for climate, but because we need the food. And many of these solutions that we're talking about are not using that much additional water. So whatever we do with the existing water that we have, we still have a potential of storing the carbon by changing the way we manage our agriculture. Going back to one of the things that I mentioned earlier, tillage, for example, it's not a big deal when you have orchards, but when you have row crops, you can reduce tillage because tillage contributes to accelerated loss of carbon. Mm-hmm. You're saving energy, but you're also keeping more of that carbon in the soil, right? So the benefits are you're getting all your agricultural benefits, and on top of that, you have some carbon storage. Got
it. Any other questions in the audience? Oh. Actually, in the back first. Yep.
Yeah, I don't know. This might come off like a bit tree hugger, but I fail to understand or envision how making a lot of infrastructure and biorefineries are going to make it net zero. Because if you're removing trees and then building more infrastructure, that's gonna generate waste and a lot of pollution, like the construction processes. And I don't see in the reports like what it's going to emit, the process of making the infrastructure for these different processes or like capture methods. And so I'm a little concerned in regards to that. Yeah, so because we have cover crops in our yard, and of course it's small, but it was a lot cheaper to just throw the seeds. So I know it's not easy, but it's also cheaper. So I don't understand like how it balances out the building of more infrastructure, like hundreds of these, and then taking out trees. So.
Yeah, that's a great question, and it is a tricky one. So with the forests in California, and you touched on this in your slides, JP, but maybe explain that again. Why is it the case that removing trees from the forest and putting them in a biorefinery, combusting them but capturing the CO2 and storing it is better than just leaving them there, right? Was that roughly the question, or no?
Not really, because
okay.
I understand that indigenous practices before, there is a natural, management that forests and that natives used to do. So I completely understand that, and not allowing for cultural burns was not a great decision. It was like not smart. I'm just concerned about like building infrastructure and like making these pipelines that are going to be invasive, the transportation, diesel trucks. So all of these things to incorporate these methods are going to be invasive to the environment no matter what. And I understand that future-wise, that's the goal, to trap, but we're already in a pretty damaged place, and I'm worried that this is just going to like make it worse because we want to build more infrastructure, and there's concrete, there is going to be a lot of like pollution generated from construction. So I'm just like, I fail to understand how doing all of this will actually balance out with the method. Like I fail to understand how it will balance out if it's going to generate more pollution.
I think those are excellent questions. And I can't give you all the detailed numbers right now, but I'll just say the emissions associated with building a facility, a biorefinery, are one time. They happen in that year, maybe 3 years that it takes to put up that facility. That facility might, though, have a 30-year lifespan. So it over the subsequent decades is doing so much in terms of removals that offsets the burst of emissions affiliated with the construction, the cement, the steel, all of those activities. So when you do the full, we call it life cycle analysis, but the full systems analysis, that one-time series of emissions is actually dwarfed by the amount of removals that are possible. Now, I agree that it's tough to think about our forests being healthier with less trees in them. But unfortunately, here we are in a landscape where we have too many trees. The growth of these trees is not increasing to the extent that the extra CO2 they're bringing down is really substantial. And the risk of having 4 times as many, that's a rough number. There are probably foresters here who would correct me, but having too many stems on an acre of land, that risk is real and growing because our climate is warming. So the risk of having those trees out in that landscape and not taking them out is enormous. And the state of California is interested in thinning regardless of BiCRS. It's really just what do we do with that biomass if we do pull those? Do we burn it? Right now, if you drive up into the Sierra, well, don't do it this weekend because there's a blizzard. But if we, if you look at many of the places where thinnings are happening, they literally make burn piles. So gosh, that's just immediately back in the atmosphere. But I want to, I think, come back to the root of what your question is that we've got to factor in all of the externalities, and that's kind of an academic word, but the trucks that are moving things around. Pipelines. We decreased the number of pipelines almost to nil. We wanted to put facilities next to where the biomass is as much as we could. We also really only looked at transport with renewable energy, so not diesel. And so that means a lot of those guardrails helped our systems analysis not create additional losses.
I'm wondering, JP, if you could sort of paint a picture for us. Let's say that we do a lot of the things that are described in this report here in California. Let's say that we manage forests in the way that's described. Let's say we manage agricultural wastes in the way that's described as opposed to how it's done today. You know, let's say we take advantage of soils and we do the DAC, et cetera. Paint a picture of that future here for us. I mean, what would the benefit be? You know, let's say we had a time machine and we're here today, we're breathing the air that we breathe today here, and then we do all this stuff and we flash forward. What differences might we notice, you know, as just human beings in the world, right?
So the first thing I'll just talk about is asthma. And that's something I developed when I came out here to California. Maybe it has to do with particulates in the air, maybe it's just how it is. But we know that the rates of respiratory issues here in the valley are very, very high. And the particulates that we breathe are partly from fires, partly due to agriculture. When we don't, I'm going to go to cover crops again, when we don't have a green cover on the land, the particulates in the air can grow. We also have a lot of diesel and trucks coming up and down the 5 and the 99. There's just a lot of air pollution, to be blunt. It's also the geology and the physics of the valley holds it in. We think a lot of the changes that we're looking at, where we have less burning, we have renewable energy sources for the transportation, we have capture on the stacks of everything, whether it's a biorefinery or some of our original industries, are going to improve our air quality. Mm-hmm. Our water quality as well. So if we have more organic matter in our soils, we have less need for synthetic fertilizers. We have more capture on site and less runoff of nitrates and some of the other things that cause eutrophication in our waterways. So those are just two simple things. But again, I don't know where Kim is right now, but Kim Mayfield, who did our environmental and equity justice analysis, she could run through a whole list of other metrics.
Let's go online again. Any questions?
Yes. When talking about giving jobs to vulnerable communities, have you also considered equitable distribution of environmental harms from the creation of new facilities?
Similar question.
We really did our best to do that. And we see a lot of upsides, to be honest, about the transition to new industries, but we obviously have to be careful because we have a lot of baked in inequalities in who benefits financially in terms of land ownership, in terms of salary, in terms of where jobs are. And on the whole, the analysis we did shows that there is more even distribution, and also that some of these more technological, the biorefineries, the BiCRS, the direct air capture facilities, where we look at where they should optimally be based on the climate, the land availability, the water availability, they are not more likely to be situated in communities that are currently disadvantaged. They're not more likely to be in communities that are currently advantaged. It's really amazingly even, 50-50, give or take, across the country. And I think that, again, I tried to say this is not a policy document, but when it becomes translated, then it becomes policy. Our policymakers, our land managers, our town mayors need to make sure that we stick to those rules, that we really are trying to even the playing field in who benefits.
Another question? Sir.
So from your slide, I recall you had about 130 million tons due to cover crops. I think that's what I saw, $40 per ton. And then you had 960 or something,
At 100.
$100 per ton. So there's more impact with the $100 per ton. So I'm just thinking this cost will be front-loaded for the $100 per ton that would give you the 900 million. And I was just curious how much front-loading you would have to achieve that result over a 25-year period to 2050. Because your $40 per ton, you can start that immediately and start doing the lower boundary entry,
Right.
Entry level to do that. So I'm just curious about the $100 per ton. How much front loading with the cost would you have before you start achieving close to that?
All right, I'm just going to admit I'm not entirely sure I understand what you mean by front loading, but let me do my best to explain.
Okay.
Go ahead.
Yeah, so you
please.
said that you spend an average of $129 billion a year to achieve that. So that's average, right? So that's not, you're going to plan, there's some front loading of that cost. You're going to spend more initially to achieve the result over the time. Do you understand what I'm saying?
I am. So let me admit some things about the way we had to do the analysis. What we like to call ecological solutions, forests and soils, that we can start tomorrow, those have per year relatively low carbon capture rates. I didn't show you the data. If you come tomorrow morning, you'll see it. But per year, they don't suck as much CO2 out of the atmosphere as we think eventually we could get to with BiCRS and DACs. That's because we've got forests right now. We've got agricultural soils. We haven't got 300 biorefineries across the country. So we can do an analysis based on today's commodity prices and what the biomass from a perennial carbon crop could be sold for, what land values are, and what a farmer needs to be able to put in their pocket to practice perennial field borders or cover crops. So because all that data exists, again, for something that starts this year. When we look at the cumulative amount that can be accumulated from here to 2050, it's quite substantial. Even each year is small, but it adds up. For bikers and for DACs, we wave a magic wand and say, okay, it's 2050, let's turn the lights on all of those facilities. And we have a calculation of what it's gonna cost across all these sectors. I'll explain this a little bit more in detail tomorrow morning, but that's the reality of technologies that we know are mature and could be built, albeit with emissions, associated with the one-time building of those facilities. But we wave that magic wand and say they exist starting in 2050.
All right. Well, thank you so much. One last question.
Yeah, thank you. I guess this is what the new biker jacket looks like, right?
Yeah.
So Mike Wolk, I run a biorefinery here in Merced, where we make biochar, bio-oils, and distillates. Really more a question for Teamrat. When you think about the 5 major reservoirs on carbon in the earth, geologic sequestrations, the atmosphere, the ocean, plants, and soils, maybe you can just sort of lay some additional context on how carbon as a new currency not only helps deal with climate security, but also affects the real confluence, the ultimate trifecta of climate, soil, and water security. I think those things are all tied to that common currency of carbon. Maybe you could lay some carbon cycle context on that. And by the way, you're all invited tomorrow afternoon. Beer's on me at Corrigan.
Where do I start? Okay. Water is agriculture. There is no agriculture without water. And the way we have been doing agriculture lately is by applying excessive water, because our soil's ability to retain water has been degraded over years of agriculture. I guess that's what you're trying to get at, right? So by returning some of the carbon that we have lost, even if we don't get any of the climate benefits that we've been talking about, the water conservation aspect of that is going to be good enough. That's a good agricultural benefit that we get out of it. You increase infiltration, which means that water is going to go deeper, and it's not going to be lost by evaporation quickly, which means plants can get to it for longer times. You will irrigate less. And even if you're not irrigating, if you improve the soil health aspect of your rangeland, right, by adding organic matter, rainwater is going to do more work for less water for you if you have more carbon, right? So yeah, the carbon will somehow be translated to water, and water is going to be translated to carbon. So at some point there might be also a positive feedback loop that we might get to.
Well, thank you. We are at time tonight, but I want to thank everyone for coming. Thank you so much. And we're looking forward to seeing everyone again tomorrow morning. So thank you. And thank you very much, Teamrat and JP.